about finding zeros and asymptotes and all that kind of thing as well. So we're just continuing in 2.6. I can't remember which year it was. No, maybe I was a sophomore or junior. Can't remember. So rational functions. We want to, when we graph these, we're going to talk about graphing, and that'll help us remember how to do a couple of other things as we graph a couple of these. So when we graph these, we want to sketch a graph. To sketch a graph, we want to find the x and y intercepts. So the x-intercepts, again, just to review quickly, x-intercepts are when the function equals 0. And with a rational function, we find that by setting the numerator. The numerator equals 0. We set the numerator equal to 0 and find the x values where the numerator is 0. So we want to find the x values where the numerator is 0 for our x-intercepts. For our y-intercepts, we just set x equal to 0 and figure out the y values. So we set x equal to 0. And we have to be careful that x equals 0 doesn't give us an asymptote or some other kind of thing that we have to pay attention to. But this is the basic way we find our y-intercepts. We want to find our vertical asymptotes. And our vertical asymptotes are where the denominator is 0. And we have to be careful that the numerator is not 0. If the numerator and denominator are 0 at the same time, we get a hole in the graph. So our vertical asymptotes are where our denominator is 0. The x values where our denominator is 0, we're going to have a vertical asymptote. Our horizontal asymptotes, we need to find them as well and graph them. Our horizontal asymptotes are, we had 3 cases for our horizontal asymptotes. And they had to do with comparing the degree of the numerator and denominator. And as we do a couple of graphs, we'll review those. I don't want to write them all out again, but we had three different ways to figure out what kind of horizontal asymptote that we had. And then we want to graph some additional points. So that we know what the general shape of our graph is going to be. And our points that we're interested in, we want to look between what did I do there? VET. Between and beyond asymptotes and intercepts. And remember that our horizontal asymptotes, that's what the function is going to do eventually. So as we go out in the positive x or out in the negative x direction, our function has to eventually get close to that horizontal asymptote. And the reason we plot those additional points is we need to know if it comes from below towards the asymptote or comes from above towards the horizontal asymptote. And for the vertical asymptotes, we need to know if the function is undefined, if it's going down, getting really small towards negative infinity, or getting really large towards positive infinity. So that's the reason we need to graph those additional points to figure out which direction our graph is going as we're getting close to those asymptotes, how it's getting close to those asymptotes. And we can also use symmetry to decide if it's symmetrical about the y-axis or symmetrical about the origin. Usually these steps are going to be enough to get a good idea of what your graph looks like. And remember that our vertical asymptotes where the denominator equals 0, that's also where our domain is restricted. So if our question asks us about the domain, we have to restrict the domain from the x values that make our denominator 0. So our vertical asymptotes and our domain restrictions are really the same thing. So these are our basic rules for graphing these rational functions. We did one really quickly yesterday. I want to do a couple more today, and one of them that we'll talk about is where we don't have a horizontal asymptote. One of our cases for our asymptotes was that we didn't have a horizontal asymptote. What we end up with there is what we call a slant asymptote, and we'll talk about how we find the slant asymptote because we have the tools to do that. So let's look at a couple of examples. We want to sketch a graph of and our function f of x is x minus 2 over x squared minus 2x minus 8. So we want to know when we graph this function, what it looks like. Now, when we have something like this where we have a quadratic, our first step is going to be to factor this denominator. So I'm going to rewrite that as x minus 2 over, and when I factor this, I get a 2 and a 4, and we're going to do a minus 4 and a plus 2. So this denominator factors to x plus 2 and x minus 4. So it doesn't matter what order you find the things in. So let's look at our intercepts first. So we're going to find our x-intercept. Our x-intercepts are where the function equals 0 or where our denominator is 0. I'm sorry, not our denominator. I'm thinking of asymptotes. Numerator equals 0. So our x-intercepts are where our numerator equals 0. So we're going to have an x-intercept at x equals 2. So our graph is going to cross the x-axis at x equals 2. Let's look at our y-intercepts. Our y-intercepts are where x equals 0. So we're just plugging 0 into our function and finding the y values. So if we plug in 0 here, all the terms with x go away, and I get that the f of 0 is negative 2 over negative 8. I'm just plugging in 0 here, which is just 1/4. So it's going to cross the y-axis at y equals 1/4. So we have a couple of points that we can work with here. Let's find our vertical asymptotes. Our vertical asymptotes are where the denominator is 0. So our denominator is going to be 0 where these parentheses turn out to be 0. So and that's why we factored this, so we can figure out where our asymptotes are. So our denominator is going to be 0 at x equals -2 and x equals 4. So we're going to have two vertical asymptotes at -2 and at 4. Now, do either of those make our numerator 0 at the same time? We have to check that to make sure we don't have a hole. So we check these, and neither of these makes the numerator 0, so I don't have a hole in this graph. And these are our vertical asymptotes. Our horizontal asymptotes. We need to remember our rules for our three cases for horizontal asymptotes. And we need to compare the degree of the numerator and the degree of the denominator. And we look at our original function and we see that the degree of the numerator is smaller than the degree of the denominator. Anybody remember what that tells us about our horizontal asymptote? What is it? Nobody remembers?
Is it no asymptote?
If the degree of the numerator is smaller, y equals 0 is our horizontal asymptote. I'm going to say that numerator less than denominator. So the degree of the numerator is less than the degree of the denominator. So our horizontal asymptote is at y equals 0. So now we can
Could you just say what if it's the other way around?
if it's
Denominator is greater than numerator. Denominator is smaller than numerator.
the denominator is smaller than the numerator,
Yeah,
then
what would that be?
we get no horizontal asymptote. What we end up with there is a slant asymptote, and we'll do an example of that as well. And our third case is if the degree of the numerator and denominator are the same. We did one of those yesterday. If the degree of the numerator and denominator are the same, the horizontal asymptote is, we find that by finding the ratio of the leading coefficients. So whatever the number is in front of the highest power of x, our horizontal asymptote is going to be at y equals the ratio of the leading coefficients. So let's start sketching. Let's sketch in our information here. So here are my axes like so. And this is not going to be a perfect graph. And I'm going to do my asymptotes. We'll do the asymptotes in red dotted lines. So we have vertical asymptotes at x equals -2 and x equals -4. I'm not going to label my points. I'm going to kind of, so there's x equals -2 for my vertical asymptote, and I'm going to go out here and say this is at x equals 4. And my horizontal asymptote is at y equals 0. So I'm going to sketch this kind of above the axis, and we'll say that's y equals 0. So this is x equals 4, x equals -2, and this is y equals 0. So there are lots of possibilities for the way our function can behave here. We know it has to go towards, get bigger or smaller towards the vertical asymptotes and eventually get towards the horizontal asymptotes. So my function could go in here, it could go in here. In between here, it could go up and down like this, it could go like so, it could go up like this. So there's lots of different ways. That's why we need to, one, we're going to plot our intercepts, and two, we're going to find some additional points. So our x-intercepts, we're only at x equals 2. So I'm going to say, we'll go out here, and here's an intercept at x equals 2. And we have a y-intercept at y equals 1/4. So our y-intercept, and I'll magnify the y-axis a little bit, and we'll say this intercept is at y equals 1/4. So now we need to know what it does between here, on this side, and on this side. So we're going to plot some additional points. So here we are at -2, so let's find f of -4 out here. So we're going beyond our asymptote. And we're just going to plug in -4 into our function. So I'm going to list some function points over here. If we plug in -4, and we calculate this out, I'm not going to go through the calculation, we get f of -4 is -3/8. So over here at -4, at x equals -4, I have a point down here at -3/8. If I wanted to, so we know that our function is negative here. So that tells us that it's going to go towards the asymptote here, and it's going to go down this way on this side. So that's where our function is going to be, on this side of the asymptote. Let's look beyond this asymptote. Let's calculate f of, so we're going out this way. Let's calculate f of 6. So if I plug 6 into my function and calculate that all out, I get f of 6 is 1/4. So out here at x equals 6, my function is positive. So that tells me that I'm going to come out this way, and my function's going to go up towards my asymptote there. And if you're not sure, you could plug in some additional points. Now let's look between our asymptotes. Here at, if we plug in f of -1 over here, and we calculate that out, f of -1 is going to be 3/5. So here at x equals -1, I'm up here at 3/5. And if I calculate f of 3, so on this side, out here somewhere, I get f of 3 equals -1/5. So out here at x equals 3, I'm down here somewhere. So my function in between, if I connect these points, is going to look something like that. And it keeps going this way. So we plot these additional points to get an idea of how the function looks, how it behaves between and beyond our asymptotes. If you're not sure, you can always plot. You could always plot a few more points to get the idea of the shape. We could plot a point here. We could plot another point out here, further out here. So if it helps you to see the graph, you can plot more points. But we plot those additional points to get the idea of what the graph looks like. Questions on that? Yes.
If it's just like rough, but you can basically tell, is that fine?
Yeah, it's the idea is to know what the shape is, and that, so like when I said out here I'm at -4 and my point is at -3/8, I didn't count down here 3/8. I said, well, it's negative a little bit, so we want an idea of what the shape of the graph is. Now if I said f of -4 is -3/8 and I plotted my point up here, you know it was totally wrong. Or if I plotted the point like way down here, kind of not accurate, but really what we want is a rough idea of what the shape looks like. And because there's so many different ways that the graph could be situated, especially between two asymptotes, some graphs here could go make a U shape, like our inverse, like our cosecant and secant graphs did. We could have a U shape going either way, or the graph could go from here and go up, kind of like our tangent and secant graphs did. They can go the opposite direction. So we need to know what they look like between our asymptotes. All right. So I just want to do one more example of where we have a slant asymptote, where the degree of the numerator is larger than the degree of the denominator. And we'll talk about how we find those slant asymptotes. So for this example, our function is y equals x squared over x minus 2. So the first thing we see here is that the degree of the numerator is greater than the degree of the denominator. So our rules tell us that there's no horizontal asymptote. But what we need to do is find out what kind of asymptote we do have. And we do that by dividing using synthetic division or long division, and dividing x squared by x minus 2. And when we do that, that's going to tell us what our asymptote looks like. So let's divide x squared by x minus 2. Well, this should be easy because we can do, since we we're dividing by something in the form x minus 2, we can do synthetic division. So I'm going to put my 2 out here, and I have an x squared, so I have a 1, and I need a 0 for the x and a 0 for the constant. So I bring that down. 2 times 1 is 2. Add 2. 2 times 2 is 4. And add 4, so my remainder is 4. So what this tells me is that x squared over x minus 2 equals x plus 2 plus 4 over x minus 2. That's how we do our division. And when we're worried about what kind of asymptote we have, we're not worried about this remainder term. When x gets really, really, really big, this remainder term gets really, really, really small, so we don't have to worry about it. So we're going to get a slant asymptote at whatever we have in this part after we do synthetic division. Yes?
I don't quite understand the synthetic division.
Yeah, me either.
I just divided x squared by x minus 2. Because that's what our rational function is division. So I just did the synthetic division. I'm dividing x squared by x minus 2. So let me write this. So divide x squared by x minus 2. So this is like we did at the beginning of the unit, where we got the problem says divide x squared by x minus 2. And I'm just doing my synthetic division. And when we divide this, the synthetic division tells you what the function is that you have left after you divide. So when we use synthetic division to find the zeros, we had a cubic function, and we ended up, when we did our synthetic division by one of the zeros, we ended up with a quadratic function. So we reduced the power by 1. So in dividing this x squared, I end up with a function that has a first power here. So it's the exact same idea. I just want to figure out what I get when I divide the x squared by x minus 2. And when we do the division, that's what this division problem tells us, that x squared plus x minus 2 is, and the 1 is going there, and the 2 is going there. and the 4 is going there. So this is what I'm left with when I do synthetic division. So I have a slant asymptote at y equals x plus 2. Whatever I get out here is my slant asymptote. So rather than a horizontal asymptote, I get an asymptote that's some other line. So now we can do the rest of our analysis on this. We'll just look at this, because once we get our asymptote, we don't need to worry about this anymore. These functions are the same, so we can just work with this like we did in our last problem. So let's find our intercepts. So our x-intercept is where the function is 0, and that's going to be where the numerator is 0. And our numerator is 0 at x equals 0. That's what makes our numerator 0. Our y-intercept is where x equals 0. And if I plug in x equals 0, I get y equals 0. So we just have the one intercept at x equals 0. Our graph just crosses our axes at 0, 0. Our vertical asymptote is where the denominator is 0. And the denominator is 0 at x equals 2. So we have a slant asymptote, we have a vertical asymptote, when we have our intercepts. So we can start graphing our function, then we'll calculate some additional points. Yeah.
So when you start it, do you have to start by finding the like the horizontal asymptote or the slant asymptote in this case?
You don't.
What if you started with like the x and y? And
That would be fine. That would be fine.
So, but then when you got to, so you could do like x, y, vertical,
Then you look at, yeah, it doesn't matter what order you do them in. I just did that one first because we'd never looked at a slant asymptote before. So I wanted to.
It's just confusing because we've never done this.
Never done it in that order. It doesn't matter what order you do it
Okay.
in. As long as you keep everything straight, you can do it in any order. You can figure out those things in any order you want. All right, so let's start sketching our graph. So here are my axes. I want those in solid black lines. And my asymptotes we'll do in dotted red. So we have a vertical asymptote at x equals 2. So I'm going to put this out here at x equals 2. And our slant asymptote, y equals x plus 2. How do we graph that? It's a line. Our y-intercept for this line, y equals mx plus b, is 2. And our slope, 1. So here, let's say this point is y equals 2. So we have a slope, a line that crosses the y-axis at y equals 2 and a slope of 1. And I'm going to sketch this in because I don't have my numbers in. But my line is going to look something like that. And that's at y equals 2. And this line is x equals 2. That's the y-intercept of this line. If we look y equals mx plus b, b is 2. So that's where it crosses the y-axis. And then my slope is, the slope is 1. So I kind of sketched a graph with slope of 1. So what we need to figure out, if this is x equals 2, we need to figure out if our function is up here or down here when x is bigger than 2. So let's plug in f of, let's figure out where our function is when x is 1. So if we calculate f of 1 and we plug 1 in, we get that my function is -1. So f of 1 is -1. So I have a point down here. And if I plug in f of 3, if I plug that in and calculate, I get 9. F of 3 equals 9. So out here, I'm up here at y equals 9. And if I plug in minus 1/2, so I'm over here, I'm just plugging that in, minus 1/2 gives me -0.1. So at y equals 1/2, I'm here. So my graph is in here, and it's in here. So the way my graph is going to look is like so. And it's going to go down this way and like so. So that roughly is what my graph looks like. We plotted our additional points to see that out here beyond this asymptote it's here, and beyond this asymptote it's in here. Questions on that one? All right. So today's what I have for today, and we have a fair amount of time to work today, is just a sheet with a bunch of problems involving